I have started to record, and I hope you are able to see my screen. Is that right?
Not yet. One second.
Oh, you haven't. So let me restart it so that you can see it. How about now? Anyone else? Are you guys able to see my screen?
I'm still not able to, but I don't know about others.
I can't either.
You can see it. Go. I don't know, Apurva, what's wrong. Maybe you can rejoin or something.
No, I can't see it.
Oh, you cannot. I see. Oh, all right. Let me just see what's wrong with this. Is weird. Anyone can confirm? I have started sharing, so I'm hoping that you can see.
I mean, also when I check the views, there's no content view, so I can't. I mean, I don't know that. I don't think you're sharing your screen yet. Should I try it? Let me try once.
Yeah, you want to share?
I'll just see if it works. I mean, okay. Does it?
Yeah,
work?
I see yours.
Okay. Can everybody else see mine?
I can see it.
Okay.
Yeah.
Okay, cool.
Well, so mine screen share works then.
Okay.
I don't. Maybe just try rejoining the meeting.
Yeah, maybe that's what I will do if I'm not able to do it. Just give me 1 minute. I'll try one more time, and then if it doesn't still work, then I'll rejoin. No?
No, not yet.
Okay, let me just yeah, I'll rejoin it.
try. Maybe try rejoining. It might work.
Yeah, I mean, that's what I've been trying to do.
And check your view. Maybe you need to go to like speaker view or grid view or something to share your screen. I'm not sure. Sometimes it doesn't work if you're like in large gallery mode, I think. I don't know.
Yeah. Yeah, let me just give me 1 more minute and then we'll do that. I thought that everything was set. I don't know, somehow.
Okay. Um.
Okay, so all right.
Okay. Try it now.
1 second.
Maybe like while we're waiting, I want to ask you what are your guys' favorite functions? Like any cool functions you guys know? Like assign 1 by x or anything.
I like the function for a hyperbola.
Oh, okay. Specifically, 1 by x.
No, like the north and south one.
The north and south one.
Like the one, not the a 1 by x one. It's like um no, 1 equals h x minus h square over a square.
Oh, okay. The general.
Yeah.
All right. Are you guys able to hear me?
Yeah, we can hear you.
Cool. Okay, I think now perhaps I will be able to share my screen. All right. How about now? Are you guys able to see it?
Yeah, I can see it now.
Yeah.
Cool. All right, so let me just 1 second. All right, so let's just start. Sorry about this delay. So far we have looked at the ideas behind the limit of a function. We looked at the struggle mathematicians had when dealing with the rate of change. That is, when two things are changing simultaneously and we want to relate them. We looked at geometric interpretations of algebraic concepts. We also looked at, in the last session, logarithms and how mathematicians related the physical reality with mathematics. We also looked at the interplay between the discrete and the continuous. You remember that? We'll come to it briefly again. And then this interplay, like we discussed, is at the heart of calculus. All right, so now what we also looked at the rate of change and quadrature. I think these are really important words when it comes to calculus. Now we are entering into, again, like I said, one of the most exciting things of calculus history, where things sort of came together. You know, this happened back in the 17th century. So we have a long way to go to come to a modern understanding of calculus, but still, this is an important epoch. So let's start. We saw before the movement of a body from point A to point B simultaneously in physical space and time. At that time, we said that the green dotted line represents a third quantity, the other two being the distance and time, right? We joined the points like A, C, D, and B with the straight lines. We could have joined them with any line of our choice, but we just choose to do it with straight lines. Now let's focus on this quantity a bit more, the third quantity, right? The one which is in the green dotted form on this graph that we are seeing. Okay, one can imagine a reasonable progression, like we talked, you know, in terms of discrete and continuous, in the values of this quantity from A prime to C prime to C double prime and so on, right? This particular quantity that is changing also with respect to time is called what? I mean, the white one is distance, right? And so the green one is?
Speed or velocity.
Yeah, we can call it speed, right? And it is useful to realize that this normal physical changes can't happen in a jerky manner. So, you know, any which way you look at it, it would be very difficult for this particular quantity that we call velocity to change haphazardly. It's very difficult to create a physical device for which, you know, the velocity changes from in very abrupt manner. So, you know, that's something true about physics, because there are limitations which are imposed on us by the laws of physics. So, you know, the progression between points that indicate discrete speeds like A prime, C double prime, etc., that needs to be smooth, right? Drawing lines on the graph paper in any manner that you want, like any lines, and achieving the values of physical entities that represents those in reality are two different things. So we need to keep that at the back of our mind. So if we have these discrete points that represent the speeds of a particular object or a particle at those 2 points in time, they can be joined by a smooth line. Now let's differ just a little bit, thinking about such physical things as speed or velocity, and consider some quantity that is just changing smoothly with respect to some other quantity as shown by a curve. So like this. Are you able to see this figure? On the horizontal axis, there is some quantity that just changes. And on the vertical axis, there is a quantity that changes as the horizontal quantity changes. Okay, so we have a smoothly changing curve or smooth curve there. We'll call it ABFC. I hope you're able to see that the points A, B, F, and C are on the curve. So as a segment, just imagine the segment BD on this particular graph or particular curve. As BD moves to right, there's something that happens, very interesting, very simple observation. The region under the curve also increases in its area, right? As the line BD becomes the line FE, you can see that the area under the curve also increases, right? It was ADB before, and now it is AFE. And as we can see that the area has increased, right? So it doesn't matter what these quantities really are, you know, the quantities on the horizontal and the vertical axes. What really matters is that they are changing with respect to each other. They can be anything real or unreal. This is like math knowing no physical boundaries. So that's what I call it, like, you know, math liberates sort of from physical reality, that you just don't care about what those entities are. Now we saw that, you know, this is what Newton started thinking about. He looked at a figure like this for a long time, and then a key insight came. His key insight was to model the quadrature, that is the area of the curve itself, as a changing quantity. Now, this is different from the quantities that are already changing. You know, the quantity that we are plotting on the horizontal axis, which is usually the time, and on the vertical axis, which can be anything, there is this third quantity. Because of just the sheer nature of how this is drawn, we see that the quadrature of this particular curve just changes. And see how simply he thinks about this. He says that like this particular quantity on the vertical axis is changing, the area under the curve is also changing. And there is no denying that fact, right? ADB becomes AFE, and as a result of that, the quadrature changes. So as the curve extends, its quadrature also increases. Now think of the rate at which the quadrature of this curve, that is the area of a region like ADB, changes. So just focus on the rate at which the area is changing. The quadrature is changing. See, quadrature is nothing. It's just like, you know, we are looking at the picture and we are saying, oh, ADB seems like the quadrature of the curve when we are at point D or when we are at point B. And when we move to point F, the quadrature has become AFE. So it is clearly changed, right? The quadrature in the case when we move from point D to E is this tiny region DEFB. Just imagine that D and E are kind of close together, where you can say that ADB has been increased by this area DEFB, right? Pretty straightforward so far, right? And now just think about what happens as D starts approaching E, or E is pretty close to D. So you can appreciate perhaps that area DEFB becomes more and more like the rectangle, right? As F approaches B along the curve, that's really very important. As F approaches B along the curve, or E approaches D along the horizontal line, we can see that the form that DEFB takes is the rectangle DEGH. Is that understandable? Is that something that you guys agree with? The rectangle DEGH is kind of approximately equal to this figure, this additional figure DEFB, right? And so what happens is that the change in the area, if we are ultimately finding what is the rate at which the area under the curve is changing. That is the key insight that Newton had. Because he modeled area under the curve, or the quadrature of the curve, as a changing quantity, the next question was, what is the rate at which that thing is changing? And how do you find the rate of one thing with respect to another thing? Well, you just divide the changes that those two entities had, right? So it's something like change in area ADB is equal to DH times the tiny change in AD, which is DE. So in the figure, D and E are kind of separate, but I wanted to, magnify it a little bit. So imagine that D and E are pretty close to each other. In that case, the change in area ADB is very much equal to DH times the tiny change in AD, which is DE, right? With me so far? Any objections?
No.
Right, so then what is happening here is that H becomes, it's pretty close to B, the approximation of DH equal to DB. And that is the rate of change of quadrature at D. Right? How do you find the rate? You just divide the changes that happen in the two quantities which are related to each other, right? So the rate at which the quadrature is changing when we are at point B is dB, right? Is that clear? This is a critical point.
Yeah, so the rate at which the quadrature rate of the curve between A and D, right, is the rate of change is equal to the value of the curve.
Right. I call it the height of the curve. So
yeah, the height of the curve at D.
So this is the important thing. You're right, Apurva. The height of a curve at a point along the horizontal equals the rate of change of the quadrature of the curve at that point. See, this is really very crucial to understand. That he just conjured up a third quantity. He just observed that, okay, these are the areas that are there. And area is also changing. And so he models area also as a changing quantity in addition to the entity or the quantity that is there on the vertical axis. So area under the curve is different from the thing that is changing. The thing that is changing along the curve is well known, right? We are measuring it, for example, the speed. or something else. Anything is fine. It just doesn't matter what those quantities are. But the one side that he came up with was this, that you take any curve whatsoever, any curve, doesn't matter. You take any curve whatsoever, the height of that curve at a particular point is equal to the rate of change of the quadrature at that point. And we gave a rudimentary proof of it. It's not really a rigorous proof, but a rudimentary proof of that seems to work. Is this clear? I mean, I really think that we need to, because this is so fundamental in calculus that, fundamental theorem of arithmetic. What we are now going to is something which has got the same kind of status as far as calculus is concerned. I want you guys to be very, very comfortable with this. If you forget everything else, or if I have the liberty to say that if there is one thing that I want you to remember, then it is this. If there is one thing that I would like you to remember, then it is this, that given any curve, the height of that curve at any point is equal to the rate of change of the quadrature at that point. So Newton was able to link, like we saw in the one of the previous slides, that quadrature was linked with the rate of change. And this is exactly how he did it. He calculated the area, and he did lots and lots of things. We will see that in one of the next slides, but this was the key insight. And this kind of leads us to what is, I don't want to name the thing, but perhaps not to stretch your curiosity too much, I would say that this leads us to what is called as the fundamental theorem of calculus. So if you understand this particular thing, if you are able to understand the moving parts of this particular line, the most important line here is that if we can understand it, and we are going to play with this particular one line, okay, and I can guarantee you that it's going to be interesting. But for now, just remember that the height of any curve at a given point is equal to the rate of change of quadrature at the same point. Okay. Yeah, so this is really what I wanted to start with, and so I have to pause a little bit and ask, okay, is there anyone who doesn't agree with this or doesn't understand this? Have I been able to convince you that in fact these two entities are the same? The rate at which the quadrature is changing is equal to the height of the curve. So if you want to find out the height of the curve, you just see at what rate the quadrature is changing. So, what I'm trying to say is that if you have understood it, then you are very, very close to having invented it. I'm not kidding. This is, imagine Newton in 1660s doing something like this. He looked at, he drew many pictures of these curves, and there were many equations which were known at the time. He applied all of his ideas to those, and he just came to this conclusion that if you know the area under the curve, if you know the quadrature of the curve, and if you are able to find out the rate at which that quadrature is changing, then it is as good as calculating the height of that curve under whose graph we are examining the area. So this is really the statement, or maybe I should say half of the statement of the fundamental theorem of calculus. Cool. So I think, we are going to have some exciting time with, talking about rates of change. And then we'll come back to this. OK, this particular slide we'll come back to. So if you have not understood, please raise your hand. I don't see any hands raised, so I think this is clear to you. I'm very glad. Cool. All right, so Apurva, you can go ahead and we will talk about this more.
Okay, so well, the first thing is that the thinking about this requires knowing about rates of change, which we haven't really gone much into yet. We know the rate of change is like, well, the rate at which something changes, right? The some quantity, right, that is changing with respect to another quantity, and we find out. So and we divide one by the other. That's how we find the rate, but the rate of change. But now we have, for our purposes, that's not enough. Now, okay, let me share my and you'll see what I'm getting at. Can everybody see my screen? Yeah.
Yes.
Okay. Okay. Great. So now we start with a little picture. Okay. We want to find out how fast a person is running. So okay, this connects back to our rate of change. So we want to find how fast a person is running. So and how will we find the average velocity of the person? How will we find that? Well, we can take the distance they travel and divide it by the time it takes them to travel that distance. That's their average velocity. Okay. So we can say that velocity is the rate of change of distance with respect to time. Really, I'm saying distance, but if we talk about physics, it's really displacement. I won't get into that too much, but it's important to know the distinction. But I'm using distance pretty loosely here. If you guys have studied physics, you know about displacement. Just a clarification. But so we can say that velocity is the rate of change of distance with respect to time, right? We can say that. But now, this is not good enough for us. We want to, let's say that we want to find the velocity, okay? How fast the person is running, okay? At a specific point in time. At a specific point in time, say 3 seconds. Let's say three seconds after it starts, okay? So this is our, say 3 seconds. And we say if we run, we can obviously find his average velocity, 20 meters in 10 seconds, 2 meters per second. So he runs, that's how fast he runs. But how fast is he running at 3 seconds after he starts? So we're asking the velocity of the person at an instant. So what does velocity in an instant really mean? Let's think about that. Like, see, if we try our normal thing, the distance the person runs in an instant. What's the distance the person runs in an instant? The distance. How far can he run in an instant? At a moment in time, how far is he running? Well, he's not really running anything in an instant, right? So he's technically running 0 meters. Remember, this is an instant. At 3 seconds, basically when you're at 3 seconds, how much distance is he running at 3 seconds? Well, he's not running any distance when you're checking the instant at 3 seconds. So because the time, right, they run it in, is also 0 seconds because it's in a moment in time. That's just an instant. So it's not, it's basically 0 seconds. So if we use the method we used previously, the distance he travels divided by the time, well, it becomes 0 by 0 because, and we can't find the person's velocity at exactly 3 seconds. So this question arises: what does the rate of change in an instant really mean? Does it exist? So yeah, how, it's an interesting question. So, but this really leads us to another question: can change occur in an instant? So this is a tough question, but let me give you my perspective. So the way I see it is, change can't really occur in an instant. But if change is occurring over a period of time, okay, we can take a particular instant in that period and say, what is the rate at which the quantity is changing at this point in time? Since the quantity cannot change in that instant, but can in the period of time, right? The rate at which the quantity is changing can be determined. Remember the rate. So even in an instant. But this is just the way I see it. So what do you guys think? Do you guys have any ideas? Any differing opinions?
Can you restate your question, Apurva?
So, I mean, how do we, can the question is, do you guys think change can occur in an instant? How about, or like the rate of change? Is there a rate of change at an instant?
Right. So I think that perhaps is paradoxical, right? I think even though we are moving during a particular period of time, but at an instant we are really stable, or we are really stationary. We're not moving. So if we are not moving, then what is happening is that the distance covered in an instant is 0, and obviously the length of time of an instant is 0.
Yeah.
So we get into this paradoxical entity, 0 by 0.
Mm-hmm. Okay. So, well, first thing we can do, right? We can plot the distance of the runner as a function of time. So we have distance on the y-axis, and it's a function of time. So suppose it looks something like this graph that I've shown. We can find his velocity, right, for each interval of 1 second. For example, like from 5 seconds to 6 seconds, right? What's his average velocity between 5 seconds and 6 seconds? We can find that by calculating the distance he runs at that interval divided by 1 second, which is the time in each interval. Right, so in terms of the graph, we're finding rise over run, right, which is the slope of the line between the values of the endpoints of the interval. So the slope of this line, right? So for example, let's take the interval 6 to 7 seconds. So 6 seconds to 7 seconds. Now, so in this example, right, the 2 points in our line are f of 6 and f of 7, So we're trying to find the slope through that. That's how we approximate it. And the slope would be the velocity, right? The slope would be the velocity of the runner over that interval. Now, we call this line that we create, we call it the secant line. So we can find the rate of change of a graph over an interval, right? By finding its slope between the endpoints of the interval. So if we can do this, right? If we can calculate the velocity based on the slope, we can calculate the average velocity based on the slope of the secant line between two different points on the function, really. If we can, find that, then our problem really dissolves to finding the slope of the graph at x equal to 3. So this graph, we want to find the slope at x equal to 3. That'll tell us the velocity of the runner at 3 seconds. But we have a similar problem now. We know how to find the slope of the function over an interval, just like we know how to find the velocity over an interval, right? But how will we find the slope at an instant, specifically x equal to 3? How? So it's another paradox. Like, what is the slope at a singular point? So we know slope between over an interval. We know well, we can find velocity over an interval, but not at an instant. So velocity over a period of time, but not at an instant. Similarly, we can find the slope of a graph over an interval, but not at a point. So our problem really, it's still there. We haven't solved it that much yet, right? So now our question is, how will we find the slope at an instant? Okay, or a slope, the slope at a point. When we say slope, we're finding the slope of a line. But we want to find the slope of the function or the slope of the secant line at x is equal to 3. So we can do one thing. Right, suppose we take the velocity of the runner between t is equal to 3 times 3 and t is equal to 4. This is not really the instantaneous velocity of the runner, but there's something we can do still. We can bring the value of the function at t equal to 4, right? We can bring that value closer and closer to the value of the function at t equal to 3. We just bring it closer and closer and keep finding the slope. So we can but as the point gets closer and closer to t equal to 3, the slope of the line will get closer and closer to the slope at the point t equal to 3. And so the average velocity we're finding will get closer and closer to the instantaneous velocity. Does it sound familiar? We've seen this before, or we've heard something similar before. But we'll come back to that. So, but this is important, right? We're bringing it closer and closer. So this might remind you of something. Hopefully it does. Okay. So we try to find the slope for a very small difference in t. Okay, let's say 0.1. Okay, and we'll call this small difference dt. Okay, dt lowercase d lowercase t. Okay, dt. We now try to find the slope, okay, between the value of the function at t equal to 3 and the value of the function at t plus dt. Okay, so what are the 2 points between which we are trying to find the slope in this case? Now, I don't want the values. I just want it in terms of t. What are the 2 points?
f of t and f of t plus dt.
So yeah, so t comma f of t and t plus dt comma f of t plus dt. So those are our 2 points, and we take the secant line through it, right? And that, we just bring it closer and closer. So since we know how to find the slope of the secant line, we find it. Okay, we just find it again. For when dt is 0.1, okay, as we see in the graph. But as we see, we can still see the difference between the left and the right graphs. So this is still not close enough. Okay. So then we choose 0.05. We can still find the slope, but it's still not the slope at t. So we try 0.01, but it's still not it's close enough. However, one thing we can see is that they may be approaching a singular value. They may be approaching a singular value, the slope at t. So this is important, okay? Although we cannot find the velocity at a singular point, we're finding the value that the velocity approaches. Finding the value that the velocity approaches. Now, we don't really care about what is the slope at t equal to 3, because we don't really know what slope at a single point means. But since we can't find the exact slope, right, we want to find the slope that the value approaches. So we're just seeing what it approaches. So basically, we're trying to find the value the slope approaches as our 2 points on the secant line as they approach each other, or as the second endpoint gets closer and closer to t equal to 3.
Yeah, so this is beginning to sound very, very simple, similar to what we were discussing in terms of limits, right? We don't really care about what the value of the function is at x equal to a.
Yeah,
we
so that's,
only are interested in the value that it approaches as x approaches a.
exactly. So that's our that's that's what I wanted you guys to see, and so we want to. So this is sort of starting to sound like limits. We can see the similarity. So we say this. We say essentially, right? We're saying that we say that the slope at a point, okay, is the value that the slope of the secant line approaches as the distance between the two x values of the secant line approaches 0. Okay, is everybody following? I'll say it again. We say that the slope at a point, right, is the value that the slope of the secant line approaches as the distance between the endpoints of the secant line approaches 0. So we're seeing what the slope of the secant line approaches as it gets closer and closer and closer to 0. Okay, so now remember, this is approaching because we really don't know like how to find the the slope. What does it really mean, right? The slope at a singular point. We don't know what that means. So we want to find what happens as we approach it. So we take the help of limits, right? So the line, right, that's created when dt, right? The dt is the distance between those two x values. When dt reaches 0, right, the line that's created is called the tangent line. The tangent line because it's a tangent to the function, right? It only touches the function at one point. Because we're trying to find a slope at a point, at a singular point, it should the line, right? This tangent line should only touch the function at one point. So that's why essentially it's called a tangent line. It only touches the function at one point. So in our case, t equal to 3. But we cannot really find the slope of a tangent line. Right? That boils down to, again, finding the slope at a point. So we can't find the slope of a tangent line. So we say that the slope of the tangent line is the value of the slope of the secant line approaches. So the slope of the tangent line, is the value, the slope of the secant line approaches as dt approaches 0. Because really, if you have just one point on a line, there can be infinite lines that can be created from that one point, or there are infinite lines that pass through that one point. So we have to say that really, as it approaches, right? As it but remember, 2 points there can only be one line between 2 points. So we say as the distance between the endpoints, right, approaches 0, our secant line approaches our tangent line, and the slope of the secant line approaches the slope of the tangent line. Okay? So everybody following along here? Everybody understands this? Are there any questions? This is important. Are there any questions? Any comments? Anything? No. Okay. Okay. Well, I'm gonna go on to an interesting definition now. Many of you might have heard of this definition, and well, maybe it's what draws some of us to calculus. So suppose you found the rate of change of a function f of x, such as the one on the left, at each point in the domain of f of x. So you found the rate of change of the function f of x at each point in the domain of f of x. So what are we finding when we find the rate of change at a single point? Who can tell me? One second. Sorry. Yeah. So when we find the rate of change, right? As we saw before, we're finding the slope, right? So at every single point, we're finding the rate of change, which means we're finding the slope of the tangent line at every single point. Remember, at different points there will be different tangent lines. So we're finding the slope of each of them at each point. Now, a function can only have this function f of x can only have one possible slope at each point in the domain. If you take this a tangent line, right, it can only have one possible slope. So this reminds us of another function, really, since we're giving it an x value, right, and it's giving us the slope of the tangent line at that x value. So it's really another function, right? So the slope at each point in the domain can be a function of x. So we have f of x, right? And the slope at each point in the domain of f of x. So the slope of the tangent line, right, at each point in f of x can so that can be a function of x. So we'll call this function that we create, right? We'll call it g of x, okay? And it's created by getting the slope of f of x, the slope of f of x at every single x in the domain of f of x, which creates, so this is creating a new function, g of x. So at some x, g of x is equal to the slope of the function of the tangent line of the function f of x at x. Okay? Does this make sense? We're creating a whole nother function, right, from the slopes. Does that make sense? Okay. So I just want to make sure everybody got this. So now I'm going to introduce a definition. So we call this function that we've created, we call this g of x function that we created. Since we've created it from f of x, we call g of x the derivative of f of x. And well, we can also write g of x as f prime of x, where the prime denotes the derivative. So the derivative, okay, of a function is another function, right? That just tells us the slope, okay, of our original function at each point. So the value of the derivative function, the value of f prime of x or g of x at x is equal to 4 will be the slope of the tangent line to f of x at 4. So that's something. That's the definition of derivative. So now, so if we do this process, right? We do this process for every single point on our graph, every single point. So we find the slope of the function at each and every x value, and for each of these x values, we graph the value on the x-axis and the slope on the y-axis, and this graph that we create is the graph of the function's derivative. So the derivative function is another function. So we can find the graph of the derivative of displacement, right? Distance versus time, and that will give us velocity. But the big thing to remember with this is that we're not associating a velocity with each instant in time. We're not associating the velocity with each instant in time, but associating the value that the average velocity approaches with instantaneous velocity. So we basically say that instantaneous velocity is the value that the average velocity approaches. We can say that. And we say that we associate instantaneous velocity with each point. So we say that so we can find the instantaneous velocity at some point, but that's slightly different than saying how fast the person is moving at some point, because a person doesn't move at a point in time, right? If at an instant in time, a person just can't move. It's like a snapshot. If you take a snapshot or a picture, right, nothing is moving in the picture. So
in the video.
Uh-huh.
In the video, I mean, like if you take a snapshot of a moving thing, the snapshot kind of freezes everything, which means that nothing is moving.
Exactly. So yeah, so nothing is really, yeah, for that. Yeah, so if you have like any picture, right, you can't say some person in a picture is moving this fast, some person in a picture is moving at 1 meter per second. You can't say that because it's just a snapshot. But so we can say like a person that's moving over a period of time has an instantaneous velocity at some period or at some instant in that period of time. And so we can, but remember, we're still not saying that the person is moving at 3 meters per second in the instant, which is 0 seconds. We're not saying that. We're saying that the value that the average velocity approaches as you take smaller and smaller intervals as over which the person is moving. The value that the average velocity approaches is the instantaneous velocity. This is a very important distinction because basically we cannot put, I mean, what is the velocity if velocity is an instant? I can't just look at a picture and say I take a picture of cars on the street. I can't say that this car is moving at 40 kilometers per hour. I can't say that. Some car is moving at 10 meters per second. I cannot say that because you're just taking a snapshot. You look at a picture. You can't really say how fast something is moving in that picture. So that's where instantaneous velocity comes in. It sounds paradoxical, and that's really important. That's really the heart of calculus. So
Right. I
our
mean, it sounds
abstract thinking,
paradoxical because it is paradoxical. I
it
mean,
is paradoxical, yeah. So
so
change always occurs over an interval of time.
right. So the
But
key things again is I think that's so thanks Apurva. I think it is kind of
I just
difficult
wanted to say
to
like one more thing.
sure.
So this is very important. You guys have to, kind of come to terms with this paradox. You guys have to come to terms with it by yourself. So this is not something that I can tell you. I can tell you, you better figure this out. You guys have to figure this out on your own. You guys have to really feel it. You have to connect with it. You have to, come to terms with it. It's not obviously I can, help you understand. Uh, I can, set you on the path, but I cannot really tell you that this is how it is. I can't explain it to you until you, understand it innately. So this one more thing, one last thing I wanted to say is that when we say that finding the derivative, right? It's an operation, right? When we find the derivative, now it's called differentiation. We call finding the derivative differentiation, and it's an operation, right? But unlike normal operations, so the multiplication operation, we take in two values and it returns a value. Okay, so we have some input and we get some output. Now these inputs, right? For example, the cube operation, right? We're saying input 4, it outputs 64. Both of these are values. But with what the differentiation operation does is that it takes in a function and it returns another function. So it's a interesting operator because it returns a function, which is something that something that's a little hard to grasp. Like, how can an operation return a whole function? It doesn't return a value of a function; it just returns a function. So that's something that we also need to think about. And there's one more thing I want to think about, tell you guys to think about. So we learned about limits. We saw their connection to rates of change. Now that we have defined differentiation, we realize one thing. Right? We can't really find the slope at every single point manually. I mean, there are infinite points on between 0 and 10. There are infinite points. So we can't do this manually. It's literally impossible. So how do we find a derivative? How do we? Okay, as you know, if I'm given a function, how do I find the derivative of that function? So that's an interesting question that we'll talk about. Next time we'll go over how to find the derivative. But I want you guys to think about that, and you guys really have to come to terms with, how change in an instant, and the fact that we can't really find the change in an instant, but we use limits, or we find what the value approaches as you get it approaches the interval reduces approaches 0, the interval. And I also want you guys to think about how operations, an operator can return a whole function. So
Right. I mean, a function typically is like a black box, right, which takes in something and transforms it to something else. Now here we have an operation which accepts a function and returns a function. So it is almost like a bijection between a function and another function. So I think these are complicated concepts or difficult concepts, but you know, we have taken a good stab at it. Really, again, the key thing to remember or to understand is that with respect to a thing that changes, there are two other things that we identified that also change. One is the slope of the tangent, or as we call the derivative of that particular changing quantity at every point. And the other changing quantity is really the quadrature of that curve. So we get sort of two things that are changing as a bonus, right? And what we are trying to do in calculus is trying to relate these two functions. One function is the quadrature, and another function is the rate of change. And we're trying to correlate these two things with each other. And we will see interesting implications of this. You know, again, how Newton came up with this, it's very, you know, if you read any of his biographies, you will see some description of what he, you know, where these insights came from. But it was not certainly only his thing. He obviously put these things together, but these things were like, you know, it was the right time that, okay, these things had to come together at that point in time because so much stuff was happening. And he just provided a fitting icing on the cake. All right, I think it's 9:50. We will, I hope we'll need some time to sort of cope with these things, you know, bringing all these concepts in your head and then kind of relate to all of them or putting them together. I hope we will use this per week for it, and I think we'll meet next time. We went over a little bit, but we also started late. So I think I'll make the recording available. Whoever missed it, please listen to it, and I think we'll meet next time.
Thank you.
Thank you very much.
Bye-bye.
Awesome. Yeah. Thank you.
Thank you.